Welcome to this explainer. Today, we're taking a super fascinating look right under the hood of software development. We're actually stepping directly into a developer's real-world code journal. We're going to explore a concept that, honestly, kind of separates good programmers from great ones. It's all about a micro-optimization. You know, a tiny, seemingly inconsequential tweak in some Haskell code that, believe it or not, carries absolutely massive architectural consequences. If you love figuring out how things work at their core and how just the smallest shifts in structure can lead to perfectly elegant systems, well, you are definitely in the right place.
Okay, let's dive right into this. How exactly do you improve code that already works perfectly fine? Well, we're pulling our insights today from a developer named Ang. Specifically, we're looking at a journal entry from June 4th, 2026. And actually, this isn't just some fleeting, random thought. This is part 153 of Ang's Notes on Haskell-Programming. Part 153? I mean, think about the sheer dedication required to get to that number. That literally tells you we're dealing with someone who thinks deeply about their craft. What's really compelling about this specific entry is that Ang isn't fixing a broken application here. There are 0 crash reports. The code was already functioning perfectly well, generating keywords exactly as intended. But Ang realized that even highly functional, totally working code can actually harbor invisible inefficiencies. It's a brilliant reminder for us that working is often just the baseline, right? It's almost never the finish line.
So to really understand this invisible inefficiency, we need to look at the specific Haskell context Ang was working in. Ang had this parent function called tokens-to-pandoc, and tucked right inside that was a little helper function called apply-index. Now the problem? It was living quietly right inside the local scope, specifically the where block of that helper function. You see, in Haskell, placing calculations inside a local where block can sometimes mean they get reevaluated every single time the function runs, even if the underlying result hasn't changed at all. Ang recognized there was a hidden performance tax being paid here. The older version of the code was generating keywords accurately, sure, but the scope of that generation meant the system was doing the exact same computational heavy lifting over and over again. Nobody explicitly told the code to waste resources, but the actual structure of it demanded it. It was basically a hidden trap sitting quietly right there in the local scope.
Now, Ang's solution wasn't some massive rip-it-down-to-the-studs rewrite. Not at all. It was a very mechanical, 3-step logical extraction. First, you've got to identify the hidden loop. You have to realize, hey, this keyword extraction is being reevaluated every single time apply index is called. Second, you literally lift that calculation right out of the local scope and move it up to the calling function, which in this case is tokens-to-pandoc. And third, rather than calculating those keywords inside the helper function itself, you just simply pass them in as a pre-calculated argument. It's a beautifully simple deduction. By just moving the keywords calculation out of that where block, Ang completely liberated the code from a totally unnecessary, invisible cycle of constant reevaluation.
And this brilliantly illustrates the change in the actual code. Previously, that apply-index function relied on a hard-coded, internally calculated variable just to get its keywords. But by simply passing in ks as a new argument, it completely transforms how the function behaves. That little ks is doing all the heavy lifting of the transition here. Honestly, it looks like a microscopic change, literally just a few characters on the screen, but structurally, it's an absolute leap forward. The updated function no longer has the heavy burden of figuring out what the keywords even are. It just happily accepts them and gets to work doing its specific job.
Which builds into an immediate, totally measurable benefit, the number 1. This single digit represents the entire new state of efficiency for this code. Because the keyword extraction was moved up to the broader scope of the calling function, again, that's tokens-to-pandoc, that extraction now happens exactly one single time, just once per run. Previously, that exact same heavy lifting was being reevaluated from the raw tokens every single time apply index was triggered. It's like, imagine a massive, heavy industrial machine stamping out metal parts, but the operator has to manually rebuild the heavy metal stamp from scratch every single time they go to make a press. I mean, it's exhausting just to think about, right? Ang's fix means you build the stamp once. Then you just press, over and over with absolutely 0 friction.
But you know, the benefits go way beyond just saving a few compute cycles here and there. This transitions us right from a microcode diff into a macro philosophy in software design. Through this seemingly minor refactor, the apply-index function became what Ang describes as pure. A pure function focuses entirely on its core functionality. In this case, purely searching and replacing keywords as index entries. It executes its specific task without needing to know anything about the external context. And let's be real, in software, ignorance can absolutely be bliss.
Apply Index no longer knows, or frankly even cares how to extract keywords from tokens. It doesn't need to read the broader state of the program at all. It just trusts that the keywords will be provided, allowing it to exist in this perfect, isolated little bubble of focused execution.
So the absolutely crucial point here is that this one, seemingly minor scoping fix fundamentally upgraded the entire architecture of this feature. It led to these incredible cascading refactor wins. Let's just look at how these compound, right? First, like we just talked about, it completely removes that wasteful keyword reevaluation, completely fixing the immediate performance leak. Second, it essentially decouples the keyword generation from the index generation. They're now two totally separate, distinct actions that don't rely on being tangled up together. And third, because they are decoupled, it makes it incredibly easy to test each piece in isolation. If you want to test your index generation logic now, you don't have to awkwardly spin up the entire keyword generator anymore. You just pass it some dummy data. It's a total game changer. It's cleaner, it's faster, and it is infinitely less frustrating to maintain.
And this brings us to the real climax of Eng's realization, and honestly, the core thesis of this entire journal entry. Quote, "A function should do one thing and do it well." This is the classic single responsibility principle, or SRP for short. Eng notes that while the initial change was, technically speaking, just a minor optimization, the real, lasting takeaway is the massive importance of adhering to SRP and keeping your functions pure. When functions try to do too many things at once, you inevitably end up with that dreaded spaghetti code. You know the kind, where pulling just one tiny thread accidentally unravels a completely unrelated part of your application. But by doing one thing perfectly well, the code's testability absolutely skyrockets, and its ability to be safely composed into larger, way more complex systems improves significantly. It really proves that what looks like a tiny local optimization is so often a profound architectural victory in disguise.
Which leaves us with this final, incredibly important question to ponder. What working code in your own projects is hiding an invisible inefficiency right now? We've seen today how code can do its job perfectly fine, all while quietly wasting resources and gradually tangling its responsibilities into messy knots. I highly encourage you to take Eng's deductive approach to your own repositories. Go look for those hidden loops. Look for those functions that are just doing a little too much heavy lifting behind the scenes. Because sometimes, the absolute most satisfying refactors don't come from fixing broken things, they come from making working things elegant. Thank you so much for joining me to explore this concept today. Keep questioning your code and happy optimizing.